Hello, everybody. It's a real pleasure to welcome Peter Harrison to our QLS CAMBAM talk series. Peter is the University Assistant Professor in the Faculty of Music and Director of the Center for Music and Science at the University of Cambridge. He specializes in computational approaches to music psychology, including cognitive modeling, massive online experiments, and corpus studies. Peter is particularly interested in the psychological mechanisms of music aesthetics, how music exploits these mechanisms. He has worked on statistical learning, creativity, musical pleasure, consonance, voice leading, harmonic syntax, and individual differences in musical abilities, among others. As usual, for questions, if you have any pressing questions, put them in the chat. And after the talk, of course, we have time for questions. All yours, Peter. Go for it. Looking forward.
Great. Thank you very much for the kind invite. I'm really happy to get to speak to you today. So I'm going to be talking about a research project of ours entitled Timbre and Consonance. And this is a project that we started during my time in Frankfurt at the Max Planck Institute for Empirical Aesthetics. And I want to thank in their absence my wonderful collaborators, Raja Margia on the left and Nori Jacobi on the right. So what is timbre? Well, we can informally define timbre as the tone color of the sound. And it's the perceptual quality that distinguishes two instruments, for example, a violin and a clarinet, even when they're both playing the same pitch at the same volume. And we know that timbre is, of course, a really complex phenomenon, and it has many components that contribute to it. But we know that a really important component is the spectrum. And today we're going to focus particularly on spectral aspects of timbre. So what does spectral mean? Well, a spectral representation is a way of breaking sound into many different components, and these different components correspond to different frequencies. We call these different frequency components partials. And in music, we're particularly interested in harmonic sounds, and harmonic sounds are special because they elicit this sensation of pitch. A sound is harmonic if all of its frequency components are integer multiples, more or less, of a common frequency. And we call this common frequency the fundamental frequency. Here's what a harmonic tone sounds like if we break it up into its different harmonics. Now, if we keep the fundamental frequency the same, but then play with the other harmonics, we end up changing the timbre, or the tone quality of the sound. The example I have on the left here has lots of energy in the upper harmonics, and it sounds like this. And the example on the right then has less energy in the upper harmonics, and it sounds like this. And likewise, we find that different instruments end up producing different spectra. For example, the flute on the left here, the guitar in the middle, and the piano on the right. So that's spectral. What do I mean then by consonance? Well, a conventional definition of consonance would sound something like this. Consonance is the sense in which certain combinations of tones fit well together when we play them at the same time. And this is very much a subjective judgment, but we do see some consistency between listeners from a given musical culture. So in Western music, the perfect fifth, for example, would traditionally be considered to be a consonant interval, and it sounds like this. Then in contrast, the tritone, just one semitone difference, would usually be considered to be a dissonant interval, sounding like this. Now we can talk about consonants at various levels of detail. On the one hand, we can talk about consonants at the level of the musical scale. So then we look at how different intervals, for example, the perfect fifth and the octave, are considered to be consonant. And here, I don't know how many of you are familiar with Western music notation, but here's the way that we're used to writing notes and chords in Western traditions. And I've plotted here consonant intervals like the perfect fifth, which is here, and the octave. They're in green. They're constant intervals. And then I've plotted other intervals like the minor second over here and the tritone in red. These are dissonant intervals. So that's consonance on the level of the musical scale. But we can also look at consonants at a much more granular level. And in particular, we can look at the tuning of individual scale degrees. So this is, given a particular musical scale, how do we tune exactly what frequencies those notes represent? Now, many different tuning systems have been designed over the centuries, and each of these attempt in some way to maximize the consonance of particular intervals within the musical scale. And I've plotted various examples here: just intonation at the top, Pythagorean, quarter common mean tone, and equal temperament. And I've plotted each scale step and its tuning as a vertical line. And you can see how there's some consistency between these different tuning systems, but also quite a lot of variation. And this reflects the different tuning systems' strategies for maximizing consonance. The question I want to talk about today is, how is consonance affected by the spectra of the underlying tones in the chords? Now, Western music theory generally suggests that the answer to this question is no. It provides just one universal scheme for categorizing intervals into consonances and dissonance. And this scheme applies equally to all musical instruments, even though these instruments have different spectra. Then on the other hand, if you look at prominent psychoacoustic theories of consonance, you'd be likely to come to the opposite conclusion. These precise computational models that we might create from these theories, they do make somewhat different predictions, but in general, they do agree that consonance should be affected by spectral aspects of these tones. But to complicate things further, if we look at recent decades of psychological studies, we then end up again with the answer of no. All of these studies tend to conclude that spectral features don't substantially affect consonance, at least not in a really meaningful way, musically speaking. So my goal in this talk today is to resolve some of this conclusion. I'm going to begin by recapping current theories of consonance. I'll quickly review limitations of previous empirical research in this area, and then I'll describe some recent work we've conducted to resolve these issues. So let's begin with these current theories of consonance. These theories can be more or less organized into three categories: interference between partials, harmonicity detection, and cultural familiarity. The first of these theories was originally proposed by the famous scientist Helmholtz in 1863. And Helmholtz claimed that a chord becomes dissonant through interactions between the partials in the frequency spectrum. He claims in particular that partials contribute most strongly to dissonance when they sit uncomfortably close together. Partials with these kinds of similar frequencies tend to produce audible beating effects. And Helmholtz theorized that beating effects in the range of about 20 to 30 hertz produce an unpleasant physical sensation termed roughness. And this roughness is what causes dissonance. Here's an example of this kind of fast beating. Then the second theory of consonance can be termed harmonicity detection. The modern form of this theory was presented by Terhart in 1974. And Terhart held that consonance perception comes from the brain recognizing harmonic spectral templates that originally developed for speech perception. Now, as a reminder, a harmonic complex tone looks something like this. Its important property is that all of its partials are integer multiples of a common fundamental frequency. And according to Terhart, the perfect fifth becomes consonant because its spectrum fits very well to a harmonic template, a template whose fundamental frequency would, in this case, be one octave below the bass note. So that's here. I've plotted this harmonic template in blue dotted lines, and you can see how it aligns very nicely with the spectrum for this perfect fifth. In contrast, then, the tritone doesn't fit very well to any harmonic template, and so we say that it has low harmonicity. The third explanation for consonance then is cultural. So according to this theory, consonance is something that is learned through exposure. A particular musical style might decide to categorize a particular musical interval as consonant, but a different musical style might equally categorize the same interval as being dissonant. And this isn't a new idea. Helmholtz talks about related ideas, but empirically speaking, this perspective is represented most recently by cross-cultural work from the McDermott lab at MIT. So these different theories end up making different predictions about spectral effects on consonance. And we can elucidate these different effects using computational modeling. First off, interference theory ends up making predictions of very strong spectral effects on consonants. Harmonicity theory predicts minor effects on consonants, whereas cultural theory only ends up predicting relatively trivial effects on consonants. So I'm going to focus on interference and harmonicity theories today. Before I describe our own work, I'll quickly review what's been done previously, empirically speaking. So, as I mentioned before, various psychological studies in the literature suggest that changing tone spectra has no effect on consonants. This first pair of studies up here by Nordmark and Fallon, as well as by McLaughlin and colleagues, they found that removing the upper harmonics from a harmonic complex tone has no effect on consonance judgments. Then the second pair of studies here by McDermott and colleagues and Friedman and colleagues, they found that a variety of different harmonic sounds yielded basically identical consonance judgments. And so as a result, many of these studies end up concluding that interference doesn't contribute in a meaningful way to consonants. So what do I think is missing from these experiments? Well, one thing is that the pitches are limited to discrete scale degrees. And as a result, the experiments never end up exploring the space in between these discrete scale degrees. And we felt that a lot of interesting information might actually be hidden in these locations. The second issue is then that individual studies tend only to explore rather limited collections of timbral manipulations. And if you've only got a small number of manipulations in a particular study, it's difficult to get much real insight into what's happening here.
Yes, quick question, Peter.
Yeah.
What is a discrete scale degree?
So on the x-axis here, we've got the interval between a pair of tones. This interval is just another word for the idea of frequency ratio. So for example, an interval of 7 semitones is a frequency ratio of 3:2. And in Western music, we often talk about music in terms of so-called scale degrees, which are conceptualized discretely. So on the piano, for example, we have something like 88 keys, and you have white notes and black notes, and they're separated at a maximum by 1 semitone, basically, or a minimum of 1 semitone. And so that's the discreteness, the discreteness of the piano. Now, the contrast to that would be if you explore spaces in between those different notes on the piano. And in theory, you can do that very easily with a violin or another instrument. But all of these psychological studies tend to only look at these categories of scale degrees.
Thank you. Got it.
So let's talk about what we can do in our own experiments. The first thing to do is to explore systematic spectral manipulations. So what we can do, for example, is change the frequencies of the harmonics in a given tone. We can change the amplitudes of these harmonics. And we can even delete individual harmonics entirely. The second thing we can then do is manipulate pitch intervals in continuous space. So for example, previous studies might have been comparing the tritone with a perfect fifth. And the tritone is 6 semitones, whereas the perfect fifth is 7 semitones. But instead of doing that, we can actually explore all the steps in between these two different intervals. And we achieve this using something that we call a dense rating paradigm. And it's a pretty simple paradigm. It's a behavioral paradigm. In each trial, we choose a random chord, and we sample this random chord densely from continuous pitch space. We play this random chord to the participant, and we ask them to rate the chord's pleasantness on a 1 to 7 scale. We then repeat this process many times with different chords and with different participants. And you might ask then, why do we ask the participants to rate pleasantness and not consonance? And this is for a couple of reasons. One reason is that if you ask musicians to evaluate consonance, they tend to respond in terms of rules that they've learned in their music theory classes, and they don't necessarily perceptually evaluate the chord on its own terms. And this is a bit of a problem if you're trying to do a perceptual study. And the second problem is that non-musicians often don't really understand what you mean by the term consonance. It's a bit of a technical term, but they do understand the word pleasantness most of the time. And it turns out that when you ask non-musicians to talk about pleasantness, it correlates pretty strongly with the concepts that we might understand consonance to be tackling. This was during the pandemic, most of all. So we ended up recruiting our participants from Amazon Mechanical Turk. And this is something which many of you will be familiar with already. It's a really popular crowdsourcing platform for psychological experiments. And all the results I'm going to report here are from US residents, but we have also done some cross-cultural work using online platforms as well. And we use a special in-house platform called Cynet that we've been developing to automate data collection. And Cynet enables us to recruit many thousands of participants spread over many different experiments. And these are the kinds of results that we end up getting for these experiments. So what I've done here is I've collected pleasantness judgments for dyads, and dyads are chords containing just 2 notes. And these are dyads made from harmonic tones, so tones where all the partials are integer multiples of a common fundamental frequency. Now we see here that the participants are producing this cloud of raw data points. So you can see I've got different intervals on the x-axis and then the pleasantness ratings on the y-axis, z-scores between participants. It's a cloud of raw data points, and these individual data points are pretty noisy, reflecting the fact that it's an online experiment, so maybe not everyone's paying attention all the time. It's a subjective task, so different people might use the scale in different ways. And consonance itself is, a subjective judgment, so people might disagree fundamentally on what's a pleasant and what's a dissonant chord. But if we get lots of participants and we then apply local averaging, here it's a kernel smoother, we do end up getting a smooth pleasantness curve plotted in dark blue. And I've plotted the actual estimates itself in black, and then I've got a 95% confidence interval obtained by bootstrapping here in blue. And that's the kind of format I'll have for all of these graphs. And what we see is peaks in this curve. And we find in this case that the peaks correspond to prototypical consonances from Western music. For example, we have the perfect fourth, which is 5 semitones, and the perfect fifth at 7 semitones, the octave at 12 semitones, and so on. Now, these red dots, they correspond to peaks obtained via a peak picking algorithm. And then these red rectangles, they correspond to 95% confidence intervals on the locations of these peaks, mainly operating as a visual aid here. So does everyone understand what this graph is conveying? It's going to occur multiple times in this presentation, so it's a good time to ask me if anything's unclear at this point. Great. Okay, and then I'm going to talk about several computational models that we use to help us to interpret the data. And these models are designed to reflect the 2 main theories that we're considering today, interference and harmonicity. And we've analyzed the data using a big variety of models representing these different theories. But today, for simplicity, I'm just going to focus on results from 2 representative examples, one from each tradition.
So question, Peter,
Yeah.
Are all the stimuli in equal temperament when you say 1 semitone, 2 semitones?
So the stimuli are all drawn from this continuous scale. So none of them are actually adhering to any particular tuning system. But when I plot semitones in this graph, I'm referring to equal tempered semitones.
Perfect, thanks.
And these are the kinds of results that we get from these models when we apply them to our stimuli. And we apply them to this continuous scale. So the models output these smooth curves, similar to what we see with the behavioral data. And here the red line corresponds to interference. And note that it has its scale reversed, so that high interference is towards the bottom, corresponding to low consonance or low pleasantness. And so we're getting very high interference for an interval of a semitone. So that's when two notes are very close together. You get a lot of this beating or roughness. And then the blue line here corresponds to harmonicity. And then the top of the plot corresponds to high harmonicity. So we see high harmonicity for constant intervals like the perfect fourth, perfect fifth, and the octave. And it's nice in that these model outputs are conceptually very similar to this theoretical curve that Helmholtz was plotting all the way back in 1863. But here, instead of being a sort of theoretically imagined curve, our curves come from rigorous quantitative modeling. Right, now I'm going to talk about the actual empirical studies that we conducted. And I'm going to be a bit tongue-in-cheek and keep a scoreboard to help us to keep track of how the results relate to these two theories that we're comparing. I'll give a theory a point whenever it successfully predicts the results of a given experiment. So let's start with the first kind of timbral manipulation, which is changing spectral frequencies. And we'll consider, first of all, a manipulation called spectral stretching. So to stretch a harmonic complex tone would mean to expand all of its frequencies so that these frequencies correspond to a little bit more than integer multiples of the fundamental frequency. So let's look at this top example here. In this example, I've stretched the tone so that the second harmonic corresponds to 2.1 times the fundamental frequency rather than 2 times. And the tone ends up sounding like this. So it's kind of bell-like. And we can apply a similar process in the opposite direction to compress a tone. And in this example here, we have the second harmonic corresponding to 1.9 times the fundamental frequency. And the resulting tone sounds like this. And before I show you the results for stretched and compressed dyads, I want to show you the results for normal unstretched dyads. And I want to have you listen to the graph that I've made. So on the graph here on the top, we have participant data. And this is basically what I showed you before, but I've removed the raw data points for clarity. Then in the middle, we've got outputs from the interference model. And then on the bottom, we've got outputs from the harmonicity model. And I'm going to play you a video. This video is going to play you all the intervals in this scale in quick succession in sort of a smooth ascent. And I want you to listen carefully to this video and try and think about what these peaks and troughs sound like. I don't know what the latency situation is in Zoom. It's possible that the video might lag behind the audio, but I'm not sure. So let's see what happens. There we go. So now let's compare this to stretched dyads. So if you look at the graph, we can see already that the consonance profile has been stretched to the right. So this was the original one, and this is a stretched one. So we see, for example, that the octave peak has been stretched from 12 semitones to 13 semitones. And if we look at the models, we can see that this stretching is predicted by the interference model, but not by the harmonicity model. So let's have a listen. Okay, I'm hearing some chat about sound. It seems like some people can't hear it, but some people are hearing everything. Okay. Yeah, some pretty unpleasant sounds here. I apologize for that. I should have got you to sign a consent form, but there you go. Okay, now let's compare to compressed tones. So as you might have expected now, if you compress the tones, you actually see that the consonance profile ends up being stretched in the opposite direction. It's being compressed. So there was a stretched version and there was a compressed version. Stretched, compressed.
So there's one more question. Did the participants listen the way we are listening, or was it isolated dyads done over many trials?
Yeah, they didn't hear anything like what we heard just now. They just heard one chord at a time. And it does make it quite different when you hear it in this continuous way, doesn't it? It's quite hard to hear a particular interval for long enough for it to actually be evaluated. Okay, so from these experiments, it's pretty clear that if we stretch or compress the spectrum, we end up getting stretched or compressed consonance profiles. This is already quite interesting because it deviates from what the Western music theorists were having us think about the universality of harmonic consonance patterns. And we find that it's consistent with the interference models, but not with the harmonicity models. So this means that we can give 1 point to Helmholtz's team, the interference team. The next thing I want to show you is results for a more sophisticated kind of tone inspired by the bonang. Now, the bonang is an instrument from the Javanese gamelan, comprising a collection of small gongs, and it sounds like this. There you go. And we use a simplified approximation to the spectrum of the bonang. The spectrum was constructed from empirical measurements by Bill Cetheres. And we model the bonang in particular as comprising 4 inharmonic partials with equal amplitudes, sounding like this. In our experiments, we then study pleasantness profiles for dyads, where the bottom tone is a harmonic complex tone, and then the upper tone is this synthetic bonang tone. And Cetheres argues that this structure reflects common instrument combinations in the gamelan orchestra. So let's see what we get. Well, we find a consonance profile that's pretty different, actually, from the consonance profiles that came before. And we see interesting pleasantness peaks at several inharmonic intervals. One here at 2.6 semitones, another at 4.8 semitones. And then we have the octave as before. And we can see that the interference model predicts the overall shape pretty well. And the harmonicity model gets some of the peaks, but also predicts an erroneous peak over here. I'm going to play you some of this now. we go. Incidentally, while we're here, I think these subsidiary peaks that we see in the behavioral data, but not in the interference model, I think probably they're explained by recognition of familiar intervals from Western music. So this would be the minor sixth, for example, and the major sixth. So based on these results, I think it's pretty reasonable to give Helmholtz's team 1 point and Terhart's team half a point. So on a score of 2 versus a half right now. Now, Billet-Cetheris had a really interesting hypothesis about the connection between the consonance patterns of the Bonang to the scales used by the gamelan orchestra. And he suggested that the consonance pattern that we see for this Bonang would be reflected in the Slendro scale. And this is one of 2 main tuning systems for the gamelan. And the tuning of this scale, the Slendro scale, it differs between gamelan orchestras, but we can approximately model it as 5-tone equal temperament. And what that means is basically you're taking the octave, which is a 2-to-1 frequency ratio, and then you're splitting it into 5 equal intervals. Now, if we plot this Slendro scale against the Bonang's consonance pattern, we find that the Slendro scale degrees end up lining up impressively well with these consonance peaks. So these scale degrees are here in grey dotted lines. And it's consistent with the idea that the scale might have developed to align well with these particular acoustic properties of gongs such as the Bonang. Okay, let's move on now to the idea of changing spectral amplitudes. First of all, I'm going to focus on a particular kind of manipulation called spectral roll-off. And spectral roll-off describes the rate at which harmonic amplitudes decay at higher frequencies. I'll start off by playing you an example of a tone with high roll-off, which is on the left here. Then in the middle, we have medium roll-off. And then on the right, we have low roll-off. The interference model predicts that if we increase spectral roll-off in this way, we'll end up eliminating most of the peaks in the consonance profile because the amplitude of the beating effects that Helmholtz talks about would be reduced. So we see here the bottom line is the original tone with low roll-off. And then up here we have a tone with high roll-off. Basically gets flat. And in contrast, the harmonicity model disagrees. It predicts that these peaks are going to remain even as we increase spectral roll-off. But let's see what our participants think. So I'm going to start by playing you a video illustrating tones with low roll-off. So as we see, like before, we get these strong peaks at harmonic intervals. Now I'm going to play you medium roll-off. And so we see that the peaks are actually being largely retained here, despite what the interference model was claiming. And then lastly, let's play a bit from the high roll-off condition. So we see that the peaks are still being retained, contradicting the interference model. And all we're seeing is basically that the curve shifts upwards. And this implies that participants do prefer tones when they have high roll-off. But the consonance profile itself isn't changing. So the conclusion is that scalar consonance profiles are relatively insensitive to spectral roll-off. And this is going to give us 1 point for Teilhart's team and 0 points for Helmholtz's team. In the next part, I want to show you what happens when we delete entire harmonics. We'll begin with a tone that contains 5 harmonics, each of which are equally weighted and sound like this. We'll then consider a tone where we completely delete the 3rd harmonic, producing a tone like this. And then finally, we'll consider a tone where we've deleted all of the upper harmonics. So our baseline tone with 5 equal harmonics looks like this. This is pretty simple, similar to the graphs I showed you earlier for harmonic complex tones. So I won't worry about playing it to you. But if we delete the 3rd harmonic, we notice something interesting, which is that the consonance peak at this minor 3rd disappears. So this was the original graph. And now this is the new graph. And interestingly, we do find that this elimination of the peak is predicted by the harmonicity model, which now has a much smaller peak than before in this location. So this is where the minor 3rd is, at 3. See how the peak basically gets squashed by this manipulation. So let's have a listen to this earlier part of this profile. See if you can listen out for the minor 3rd. And why not compare that to the full version? There we go. And it's worth noting that the interference model is not predicting that effect. Interference model is just flat in this region. Okay, and then lastly, this is what we get if we delete all of the upper harmonics. So at this point, many of the peaks have disappeared from the behavioral profile, but we do still see peaks at the 5th, which is this one, and the octave, which is here. And these are very clearly contradicting the predictions of the interference model. So let's have a listen. There we go. So to conclude from those 3 experiments, deleting harmonics changes the consonance profile, but these changes are predicted better than the harmonicity model than by the interference model. So now this means that Teilhart's team actually gets another point. Now, in those previous experiments, we've been focusing on this global scalar consonance profile, but I want now to zoom in and think about the tuning of individual scale degrees. Let's start off by considering the major 6th. So this interval corresponds to 9 semitones. Harmonicity models predicts that listeners should prefer what's called a just-intoned major sixth, which I plotted here with this vertical line. Just intonation just means that the chord corresponds to an exact frequency ratio, something like 3:2, 4:3, or 5:4. And the reason the harmonicity model thinks listeners will prefer this is that a just intoned major sixth fits very well with an idealized harmonic template. Equal temperament, though, is what we normally get in much of today's Western music, especially in pop music. It's what most of your pianos will be tuned to. And that's what you get when you subdivide the octave, this 2:1 frequency ratio, into 12 exactly equivalent intervals. And according to the harmonicity model, listeners should be less keen on this equal tempered interval because it's quite a lot less harmonic. It turns out that the interference models also make similar predictions about this discrepancy between just intonation and equal temperament. But what we see in practice when we actually play these chords to listeners is something quite different and quite interesting. We weren't really expecting to see this. What we see is a dip in preferences at the just intoned interval. But instead of seeing a peak at equal temperament, we see two peaks, one either side of just intonation. And it definitely doesn't align with equal temperament. So let's have a listen to these intervals. We can repeat this same experiment with different intervals, like the major third and the octave, and we get similar kinds of results. And if we listen to these examples and try and intuit why we might have preferences for these slight deviations from just intonation, it seems quite plausible that listeners are enjoying the slow beating effect that you get when an interval deviates slightly from just intonation. And this is pretty interesting because it implies that tuning systems shouldn't be striving for these absolutely pure, just intoned intervals after all. Actually, being imperfect is a virtue as long as that imperfection is not too large. Let's ask now what happens to these effects if we delete the upper harmonics from the tone. Well, we find that the preferences for small deviations from just intonation disappear entirely. And if we think back to our hypothetical explanation, this makes quite a lot of sense. This elimination of the peaks can be explained by the fact that the upper harmonics were the ones that were responsible for these slow beats that the participants were previously enjoying. So let's have a listen to this version without upper harmonics. So to sum up those few experiments, we're seeing that strong upper harmonics cause listeners to prefer slight deviations from just intonation. And it seems this could be explained by a preference for slow beats. And then deleting the upper harmonics from the tones seems to eliminate these slow beats and hence the preference effect. I'm going to give Helmholtz's team half a point for this, to be sporting. It seems that beating is important for tuning, But the nature of this effect is more complex than previously acknowledged. It isn't just that listeners dislike beating, but it's that they dislike beating in this particular frequency range and actually like it in this other frequency range. Now, the experiments I've talked to you about so far have all been about chords with just 2 notes in them, chords that we call dyads. But much of Western music is comprising chords that have many more notes in them. So it's an important question to ask is whether we also see spectral effects for larger chords, such as triads. And a triad would be a chord with 3 notes in it. Well, we studied this with a new adaptive technique that we developed in the Max Planck during my time at Frankfurt, techniques called Gibbs sampling with people. And it's actually a pretty simple technique. It's based on a continuous adjustment task where participants have to adjust an individual interval in a chord to make it as pleasant as possible. And here's what an individual trial sounds like. And the important thing is that this GSP process is an adaptive paradigm. So the stimuli presented to one participant depends on the stimuli presented to previous participants. And the idea is that the participants are working together to explore a stimulus space that might have more dimensions than you could feasibly explore with a simple, exhaustive, non-adaptive paradigm. And if we apply this paradigm, we end up getting very rich 2-dimensional plots that kind of look like images from space telescopes. But these plots show us the consonance and dissonance of different triads in continuous space. So in this map, light patches like this one, they correspond to consonant chords, whereas dark patches correspond to dissonant chords. So here there's a hotspot at 7/5. That means the lower interval is 7 semitones, which is a perfect 5th. The upper interval is 5 semitones, which is a perfect 4th. And that's basically a chord with no third, so it's a power chord, basically. And something we see quite saliently in these kinds of plots is an octave diagonal. And this corresponds to chords where the top tone is an octave above the bottom tone. And we can apply the same kind of visualization for our computational models. So here I've got outputs from the interference model and outputs from the harmonicity model. And we can see that the outputs of both the interference and the harmonicity model have this octave diagonal as well, this clear consonance of chords where the bottom tone is an octave away from the top tone. So if we replace these harmonic tones with compressed tones, we see, as you might have expected from before, that this octave diagonal ends up being squashed. So that was the original, and that's the squashed. So it's moving towards the bottom left corner. And this is something that we see is predicted by the interference model, but not by the harmonicity model. And conversely, if we replace the tones with stretched tones, we end up seeing a stretched octave diagonal, again, as predicted by the interference model, but not by the harmonicity model. So our conclusion from this is that spectral manipulations can indeed change consonance profiles for triads, not just dyads. So it can be relevant for the more complex kinds of chords that we see in real Western music. Right. I'm going to recap what we've covered today. We asked whether spectral content affects consonance, and the answer is very clearly yes. We first looked at changing the frequencies of the harmonics, and we found that we could successfully elicit preferences for inharmonic intervals. We then looked at changing the amplitudes of the harmonics, and we found that just changing the amplitudes doesn't change the consonance profile very much, it just changes the overall pleasantness. But something different happens if we delete entire harmonics. We find that, in contrast to what previous studies have claimed, we do end up losing peaks from the consonance profiles. And we also ended up identifying these interesting patterns of tuning preferences in the neighborhood of just intoned intervals, this sort of double peak effect. And with these patterns then disappearing once we remove the upper harmonics. And then in the final part, we looked at whether these spectral manipulations can affect consonance profiles for triads. And we found that the answer was yes. So compressing or stretching the tone spectra yields compressed and stretched preferences, respectively, as we see in the following plots. And then all the time we had this scoreboard going along to keep track of how well different psychological models predicted the results from different experiments. And we found mixed results for both the interference and the harmonicity approaches. And the interference approaches do better on some experiments, whereas the harmonicity approaches do better on other experiments. And it seems more or less to be a tie. So one potential take-home message is that both interference and harmonicity are likely to contribute to consonance perception. And if we assume that both these factors are at play simultaneously, then we can actually explain the results of many of those experiments. But an interesting thing we can then do is to use these results to improve the theories and the models themselves. So one aspect was that idea we talked about earlier, that slow beats are potentially perceived as pleasant, and this can cause listeners to prefer slight deviations from just intonation. And we've now been incorporating this feature into our updated interference models. And then a second observation is that interference models don't predict any beats between pure tones at mistuned harmonic intervals, like the fifth and the octave. But if we listen very carefully, we can often hear beats at these mistuned intervals. Let's just hear some of this. It's going to be quite subtle depending on your listening environment. But if you've got some good headphones on, and maybe if you don't have Zoom's audio compression algorithms going, you can end up hearing these things. So we're currently exploring these possibilities in ongoing work. Now, as we wrap up, I do want to mention this important question of cultural universality. So if I had to speculate, I would hypothesize the following. The underlying psychoacoustic effects that we're talking about, things like beating, they should be shared cross-culturally, but their aesthetic implications are likely to vary across cultures. And we know already, for example, that beating isn't universally considered to be unpleasant. So to give one example, here's a performance on the midriz, which is a Middle Eastern instrument comprising two pipes. And here the beating is really treated as this positive, virtuosic technique. It's something that is being celebrated, not avoided. So let's have a listen. So thanks very much for listening. I really appreciate the attention, and I look forward to hearing any questions you might have.
Thanks a lot, Peter. That was great. We have time for a few questions. Anyone? Yes, Adrian. And then Oscar.
Oh, I think.
Oh, that was a buy, not a question. Okay. I always misinterpret those. Yes, there's a question from Simon. Yes, go for it.
Hi, thanks for justifying getting fancy computer speakers, first of all. Second, I didn't get the unacknowledged beats discussion. So it seems, so I didn't get exactly what went in your models and why it didn't capture these beats that were reasonably, hearable. So what's missing in the model to capture those beats?
Interesting story here that you're right, I didn't dig into at all. There is this series of interference models that have been presented in the literature. The earliest ones are very much idealized models. And what they do is they take spectra represented in the kind of way that I represented them. So just approximating a tone as a discrete set of partials, maybe just 10 or so. They perform a function that iterates over all pairs of partials in that spectrum and computes the contribution of those pairs, and that's as a function of the distance between them, with this distance in units of, so related to the sort of inner ear structure. That's a very much a sort of idealized version, and it doesn't predict any beats at these. There was this journey to create models that were increasingly more and more biologically realistic. And these models would, for example, incorporate simulation of the different filters of the inner ear. They would involve doing things like applying Hilbert transforms to actually estimate the true envelope of the sounds and use that as beating. And some of the copular hydrodynamics and so on. And what I found interesting in work that I didn't talk about today, when I went through a very large number of these different models and then evaluated them in the context of harmonic chords or harmonic tones, is that the more and more realistic these models became, the worse and worse they performed. These effects, but there's something else. So I think that certainly something that I would like to do is revisit these more realistic models and try and work out why they were failing on the easy questions and see whether they might offer a good answer to the hard questions.
Thanks, Peter. Any other questions? I have a list, but we don't want to keep everyone here, so we can turn off the recording if no one else has other questions. Anyone else?
Yeah, I have a question.
Yes.
So when you were playing an interval for participants, we saw like pleasantness as a function of the separation between the notes in the interval. But is there a difference between pleasantness based off of like where that interval starts? Like, for example, 440 hertz as the base tone versus like 443.2 hertz. Like, do we have like a natural affinity for frequencies that have round numbers hertz, or is that like maybe culturally conditioned into us, or is it just the separation between the tones that matters? I can't hear you.
Yeah, so we are missing your audio quite a bit during the question answer session, but not during the talk. Could be Zoom. No, we can't hear you.
I thought it was working so well all the way through.
Okay.
Yeah, good time.
I've
Good
changed.
timing that it happened at the end, but we are not actually hearing you.
I've changed it now. I can see
Yes,
the
this
green
works.
thing.
Yeah.
That's so weird. Okay.
That's good.
Thank you for letting me know. Great question from the room there. Thank you.
They do look like.
So we do know that pleasantness actually depends on the absolute pitch height of notes. In particular, If you play a particular chord very low down with a very low frequency, then it does end up making certain intervals sound dissonant when previously they were consonant. But the amount of transposition you have to do to achieve those effects is quite large. So in the context of just small amounts that we're talking about here, maybe 400 hertz versus 500 hertz, we don't really notice any difference. So in this context of this experiment, we focus just on this middle range that's representative of what we normally have in Western music. I can see a few interesting questions in the chat here as well, so I might answer these now. So there's an important question about bias in who applies to SciNet. So this is an important question. So sampling bias, the sense in which the participants that we get through these online studies might not represent the kind of population that we want to get. Now, of course, it's a whole spectrum here. So on the one hand, you can run these experiments in a very local sense with undergraduate students from your department and so on, which are hugely homogeneous in terms of age and cultural backgrounds and this kind of thing. We think that these kinds of online studies with Mechanical Turk and other crowdsourcing platforms do a fair bit better than those kinds of convenient sampling. So there's good papers out there looking at how these demographic splits and so on. You do get a good age range and so on. You do get some varieties in socioeconomic backgrounds. But of course, it is a particular kind of person who wants to do these kinds of online studies. And so they have to be complemented with maybe more targeted cross-cultural studies where you're being quite careful about your sample groups. We find here that if you're focusing on these kinds of psychoacoustic effects, and if you're focusing on sort of westernized listeners, we find quite a lot of consistency as far as we can think. But we definitely want to follow this up with more targeted cross-cultural work.
So there's that one last question, and then we can turn off the recording.
Okay, great. Well, there's a final question in the
Yeah.
Zoom, which says, here we go. How would the interval / chord function within a harmonic sequence, as you might have in natural music, how would this interfere with the pleasantness with the diaton chords? So that's another really important question. So we've been doing these chords in very isolated contexts, not in a piece of music. And real music has this dynamic sense. And there's been some work on this. There's a study by Johnson, Laird and colleagues where they do have an experiment involving this consonants in the context of chord sequences. And it does get more complex and interesting here. So there is, in one sense, sort of additive phenomenon. So you can have consonants coming in part from the sort of isolated sensory consonants of an individual chord, but there's also an additional component, which is how well does that chord fit in with the previous chords that came. And that harmonic fit can stem, it seems, partly from sort of syntactic questions, what have you learned about the grammar of chord sequences? Also potentially from some kinds of psychoacoustic concerns where you compare the spectrum of the current chord to the previous chord. But there's also this really complex story that is barely explored by music psychologists to do with the sense in which composers can manipulate dissonance to create tension within a piece. So for example, a lot of Western music in the classical era uses the notion of suspensions. So these are dissonances that you prepare in a certain way, you sort of experience them and then you resolve them. So these moments of like creating dissonance and then resolving it. And this creates this particularly appealing aesthetic effect. So yeah, it becomes really interesting when you have these dynamic questions, that's for sure.
Great. Thank you very much, Peter, and thanks for the great audience. And yeah, we can turn off the recording now.